All right, we are on chapter 14. We're going to be looking at equilibrium, and this is the first video for that. So I want to draw your attention to the picture that's on this slide, okay? And you can see some water coming into this container, and you can see some water going out as well. All right, so we're going to look at equilibrium. Oftentimes we have just written down reactions, and we just assume all of the reactants will go shoop and turn into products. Does that really happen? And we looked at rates in the previous chapter and what affects the rate of a reaction, and we looked at things that we could do to speed a reaction up. All right, so let's look at this picture, and the water coming in, we're going to be calling the forward reaction, okay? Now, if there was no water in the tank when we started, you could see that the forward reaction would start, and the reverse reaction, when the water's coming out of the tank, wouldn't be going at all because it has to reach some level. You can see kind of where that little spigot is. It has to reach some level before water can start coming out. All right, so over time, water's coming in, water will slowly start coming out. At some point, the rate of water coming in and the rate of the water coming out will be equal. We would say that is when we reach equilibrium, okay? And you can think about what does that effect have on how much water that tank is holding. As the rate becomes equal in to the rate out, is that water level changing at all? All right, so that's what we're going to be kind of looking at when we're thinking about equilibrium. All right, let's look at the next slide. Pick this up here. All right, so we've hit and talked about equilibrium a little bit in previous chapters. And one thing that we want to talk about is dynamic equilibrium. And this is when you have the rate, okay, of the forward reaction being equal to the rate of the reverse reaction. This is our definition. Make sure you circle the words rate and equal and rate. All right, so the rate of the forward is equal rate forward equals rate reverse. All right, so here we go. We can look at this reaction here. We have SO2 plus O2. They go and make SO3 gas, okay? But now the reverse rate can start going as well. And so now as you are starting to make some SO3, all of a sudden it's going to go the other direction and then start breaking apart into SO2 and O2. Now, when you reach equilibrium, the rate that you're making the product will be equal to the rate that you're making the reverse. What does that mean as far as the concentrations of the reactants and products? Does that mean that they're equal to each other? No, okay? So that's one thing that you have to make sure you understand. Equilibrium does not mean that the concentrations are equal. It's that the rates are equal. And so if your rate of forward is equal to the rate of reverse, once you have reached equilibrium, you shouldn't see a change in concentrations anymore. They should stay steady. All right, so reactions that reach equilibrium, okay, are often called reversible reactions. This is when the reverse reaction also contributes to the overall amount of products that you make and reactants that you make. So chemical reaction, the reaction contributes significantly to the overall reaction. Let's look at these pictures right here and see what happens. All right, so in the first one and the second one, these are both two different reactions. One is N2 and O2 go and make NO, and the other one is SO2 plus O2 make SO3. They're both at equilibrium. That leads us to when we say that the rates of the forward equals the rate reverse. Okay, so they have reached equilibrium already. Now look at the initial, where they start and where they finish. Now the first one, it started with some reactants, and then when the reaction stopped, okay, when it reached equilibrium, only a small amount of the reactants turned into products. And the second example, okay, you start here with all reactants. As the reactants turn into products, you finish and you have a lot of the reactants have turned into products. There's still some reactants there. When the concentration of reactants at equilibrium is greater than the concentration of products, you would say that the equilibrium lies to the left-hand side, okay, and note that the left-hand side is the reactant side. And when we say that the equilibrium lies to the right, that means that when the equilibrium is reached, when reaction, the rate reverse and the rate forward are equal to each other, at that point when the equilibrium lies to the right, you have more products. The product concentration is higher. All right, so let's look at an example. So the main thing here, just because you have a system that is in equilibrium, that does not mean that your concentrations of reactants and products are equal to each other. All right, so I have this drawing right here, and we're going to pause. We're going to let you kind of work through this, and then we'll come back and go over the answers. So we have 1, 2, 3, 4, 5 different reactions taking place, A through E here. The reaction is A turns into B, and A is the red little balls and B is the blue. And so I want you to go through each of these and say, does the equilibrium lie to the left, the middle, or the right? So for each of these, I want you to write either 1, 2, or 3. You want to look at how they all start. They're all starting with only reactant, and then at equilibrium, when the rates of the forward and the reverse are equal, where does the equilibrium lie? All right, so take a little bit to pause, come back with an answer in a couple seconds. All right, hopefully you have your answers as well after that pause. You want to look at where the reaction starts, where it reaches equilibrium, and see what do you have most at equilibrium. So if we look at the first one, A, you can see at equilibrium we still have a lot of the red dots. So we still have a lot of reactant and just a little bit of product. So for this one, equilibrium lies to the left, which is the reactant side. All right, and B, you look at that one, now we've made a ton of product when we reached equilibrium, just a little bit of reactant is left, so the equilibrium lies to the right. The next one, we have equal amounts of reactant and product. Now note, all of these are in equilibrium, but this is the only one where the concentration of reactants and products are equal to each other. So we would say that the equilibrium lies to the middle. All right, in D, okay, you can see that we have mostly the blue, okay, which is the product, a little bit of the reactant left, so equilibrium lies towards the product side. And the last one we have again where we have more of the red dots than the blue, so equilibrium lies to the left for that one. All right, so which reaction essentially doesn't go, okay, doesn't go at all? We would probably look, and we're going to look here for the one that's mostly to the left, all right? So the furthest to the left, we would say essentially doesn't go. I would say that would be A here. All right, you can see in A we have mostly red dots, just one of the product. And then which reaction essentially goes to completion? Which one have all the reactants turned into products? I'm now looking to see which one has mostly the blue, which is the product, and I would say that would be B. All right, I hope that helps kind of set our tone for equilibrium. Concentrations could be more to the product side, more to the reactant side, or in the middle when equilibrium is reached. The definition for equilibrium is when the rates of the reverse and the forward reaction are equal. We'll look into more of it in the next video.